Hello APC Mechanics students, today we will solve the past paper FRQ 2015 exercise 1. Then let me start. Then this is exercise 1. A block of mass m is projected up from the bottom of an inclined ramp with an initial velocity of magnitude v0 as shown here. The ramp has negligible friction, this is important for us, and makes an angle theta with the horizontal. A motion sensor aimed down the ramp is mounted at the top of the incline so that the positive direction is down the ramp. Pay attention that the positive direction is down the ramp. This is the origin. The block starts a distance d from the motion sensor. Then initially the block starts from this point at a position d from the origin. The block slides partway up the ramp, stops before reaching the sensor, and then slides back down. So basically, upon the upward motion along the ramp, it will stop somewhere here, then it will slide back down. Now part A, consider the motion of the block at some time t after it has been projected up the ramp. Express your answer in terms of md v0 t theta and physical constants as appropriate. So now, in the following parts, whenever we determine an expression, we need to make sure that this expression is being expressed in terms of these and physical constants as appropriate. And a perfect example about this one would be the gravitational field strength G. Then we need to determine the acceleration A of the block. We know that, first of all, the positive direction is down. So let me first start and say that for a free falling body, the acceleration is given by G. For a falling body on a ramp, that would be given by G sine theta. And if we have friction, the modification would be given by G sine theta minus mu k cosine theta. So basically we know that because this is the case of a frictionless ramp inclined by theta, then the acceleration would be G sine theta. Because the positive direction is down, then it's given by plus G sine theta. If the positive direction is given to be up, then that would be given by minus G sine theta. Then we know that our expression would be this, but if you pay attention to the exercise, they're telling us to determine, and determine means we need to derive. And this can be done basically by considering Newton's second law. Then let me say apply in Newton's second law, which is a big law. And this is done first by stating that F naught is given by MA. Now, in order to deal with the Newton's second law, we need to utilize the forces that are acting on the block. They didn't ask us to represent an FPD, so let me do it here. So let me say this is the x-axis and that's the y-axis. So this is the block at any instant. What are the forces acting on the block? We have the pull of gravity, which is down. We have the normal push. So in this case, the total forces acting on the block would be the pull of gravity plus the normal push equals to MA. Now remember that this is a vector equation. It will give the birth of two linear equations whenever we're projecting it along the x and along the y. Because the acceleration happens to be along the x-axis, then we're going to project it along the x-axis. We know that if the ramp is inclined by theta, then this is the angle theta. Now let me say projection along the x-axis. Now the pull of gravity, because it's pointing in the positive direction, which is down, that would be Fg given by, so that would be cosine theta and that would be sine theta, plus 0, the normal push has no projection along the x-axis, that would be Ma, so Mg sine theta would be equal to Ma. Now m cancels with m, and indeed we have that the acceleration is given by g sine theta. Since this is a derived expression, let's refer back to the question. Indeed, it has been expressed in terms of the physical constants g and the angle theta. However, sine is a function, so don't expect that they will tell you express your answers in terms of the sine or cosine functions. Now we know that because the acceleration is constant, then the block along the upward or downward motion, it will obey uniform varied motion. Now they're telling you to determine in idea 2 an expression for the velocity v of the block. Now the final velocity of the block is given by vx0 plus axt, knowing that the block initially has a velocity v0, and notice that velocity v0 is pointing in the negative direction. So they're telling us the expression of v, then let's use the same notation. That would be replaced by v, and that would be minus v0. Why here we have the minus sign? Simply because it's being projected in the negative direction, and we know that the acceleration is pointing in the positive direction, given by g sine theta multiplied by time. And indeed, if you check, it's being expressed in terms of v0, physical constants theta and t. Now in idea number 3, we need to determine the expression of the position x of the block. Also, this can be done by referring to the type of motion. We know that in this case, the position, horizontal position, position along the x-axis is given by x is x0 plus vx0t plus half axt square. Now initially the block starts from a horizontal position away from the origin in the positive direction to be d. Then this x0 would be replaced by d. The initial velocity is negative, given by minus v0 multiplied by t, plus half the acceleration is given by g sine theta multiplied by t squared. Then that would be the answer for idea number 3. Okay. Now in part B, we need to derive an expression for the position x minimum of the block when it is closest to the motion sensor. Express your answer in terms of m, d, v0 theta and physical constants as appropriate. So whenever they mention minimum, it means it belongs to a bigger class of x minimum, and these can perfectly handled via derivatives. We know that the derivative of the position is velocity, so we need to vanish the velocity, and this is reasonable. Why? Because they're asking for the minimum position of the block when it's closest to the motion sensor. So as it goes up the ramp, it will reach a point before it goes down. This point is characterized by v is equal to 0, which is the minimum position with respect to the motion sensor. So you can understand it both ways. Now we need to set v is equal to 0. Now we have determined the expression of the velocity, and it's given by what? It's given by that. So let's vanish this expression. That would be given by minus v0 plus g sine theta t equals to 0. And basically here we're solving for what? We're solving for time, which is the time required for the velocity to vanish, because all of these are constants. Then solving for time, isolating time, that would be given by v0 divided by g sine theta. Now why we're solving for time? Because we need to find the minimum position, and the position explicitly depends on time. So the time that we have found here would be replaced in this position. Then let's do that. The position is given by d minus v0 multiplied by t plus half g sine theta multiplied by t squared. That would be perfectly given by minus v0 multiplied by v0 divided by g sine theta plus half g sine theta multiplied by v0 divided by g sine theta to the power of 2 So now notice that v0 multiplied by v0, that would be v0 squared. So d minus v0 squared in the numerator divided by g sine theta. Now what about this? This is very similar to the thing that we do in the projectile motion. So it would be v0 squared divided by g squared sine squared theta. And in the numerator also we have g sine theta. So basically this will cancel with the power 2, this will cancel with the power 2, so we're left with plus half v0 squared divided by g sine theta. And notice that here we can factor out v0 squared g sine theta from both expressions. We're left with minus 1 plus half, and that would give us minus half, and this can be written as d minus half v0 squared divided by g sine theta. So the minimum position, that would be the minimum. Why we're pretty sure that this is the minimum? Because we have vanished its derivative, we have determined the time and replaced it in the position. Then that would be the expression, and let's check again that it's being expressed in terms of d. v0, physical constants g and theta. However, they mention mass, but always remember and forever that they will offer you different options in order not to be limited or not to check that your answer whether it's correct or wrong. Alright, then this is it for this part. Let's move on. Now on the axis provided below, sketch graphs of position x, velocity, and acceleration a as function of time for the motion of the block while it goes up and back down the ramp. Explicitly label any intercepts, asymptotes, maxima, or minima with the numerical values, all algebraic expressions as appropriate. Then we always follow the path or the trend of a to v to x, 0 to constant to linear to quadratic. Basically, we know that during the upward motion and the downward motion, that won't change the value of the acceleration, because the acceleration depends on the force, and the force is gravity, and the gravity is a action at a distance, so it won't change. Acceleration will be always pointing down, which is positive, which means that the acceleration is positive. Velocity will be linear, x would be quadratic. So the correct representation of the acceleration would be a positive constant like that, and we need to label this intercept or this value given by g sine theta. This is it for a. Now we know that v is gonna be linear. Knowing that initially during the upward motion v has started with a negative value, which is given by minus v0, so we will start with the value of minus v0, and due to the symmetry of the problem we expect that it would end back at the ramp with the speed also v0, so it will be something like that. Okay, and now for the position, so we know that if v is linear, the position would be quadratic. So now because the acceleration is positive, so let me say here v is linear, so it would be a parabola either open up or open down. So because the acceleration is positive, it will be open up, so it's gonna be either like this, like this, like this, or like that. Initially the velocity is negative, which means it will decrease, and after that it stops. So here won't change, then the velocity becomes positive, then the position will increase, then the shape of the curve would be something like that. Now let's try to label the intercept. Initially the block started distance d away from the motion sensor. It will reach a position given by x minimum that we have determined, and again when it reaches the bottom of the ramp it will reach again a distance d. Now part d, after the block slides back down and leave the bottom of the ramp, it slides on a horizontal surface with a coefficient of friction given by mu k. So let me draw a horizontal surface. This is the horizontal surface, that would be the block, and because it's traveling to the right, let me choose the positive direction to be to the right. And in this case we have friction between the level surface and the block, so the level surface would be represented here if you want. Now derive an expression for the distance the block slides before stopping. Express your answer in terms of md, v0, theta, mu, k, and physical constants as appropriate. So we need to determine the distance. This can be done using kinematic equations. But remember that in the kinematic equations, because we have friction in this case, it means it involves acceleration. The acceleration can be determined using a big law, which is a Newton's second law. Then let's utilize the forces that are acting on the block whenever it's moving to the right. So let me draw here a simple FBD. So this is the horizontal and that's the vertical. Now what are the forces acting on the block? We have the pull of gravity down, being balanced by the normal push up. And we have the friction to be acting opposite to the direction of motion. Then let me say this is Ff, the force of friction. This is the pull of gravity. That's the normal push. And now we're ready to apply Newton's second law. So let me say apply Newton's second law. And that would be F net is given by MA. What are the forces acting on the block? We have friction. We have the normal push. We have the pull of gravity. And that would be equal to MA. Now projection along the horizontal. So friction, it's acting in the opposite direction. So minus FF. Normal push has no projection. That would be 0. Pull of gravity has no projection. That would be 0. And that would be MA. And remember that we're searching for the value of the acceleration because we need to find the distance. And in the distance, we know that from kinematics, most of the expressions, they involve acceleration. Then in this case, acceleration would be given by minus friction divided by the mass. And you know that friction in this case is given by minus mu k Fn divided by m. And also we can say that the normal push is equal to the pull of gravity because they are balanced forces. So that would be minus mu k. We know that the pull of gravity is given by mg, so the normal push is equal to the pull of gravity is equal to mg divided by m, so this cancels with that. Then the acceleration is given by minus mu k mg. Because mu k is constant, g is constant, then the acceleration in this case is constant. Then we know that the type of motion is uniform varied motion, and we can use the equation given by v0, vx square is v0 or vx0 square plus 2a delta x, and we're searching for the distance given by delta x. Now before stopping, so the endpoint would be stopping, then that would be 0, the final velocity is 0. Now what about the initial velocity? Remember that from the early beginning of the problem, the block has been projected up with velocity v0. It will reach here some point, and during the downward motion it will leave the ramp with the velocity v0 with the magnitude given by the speed, which is v0, before it starts traveling along the level surface. So that would be v0. Now whether minus or plus, we don't worry, because here if we also have a minus sign regarding the direction, that would be to the power 2. However, we're taking the positive direction to the right. As it leaves the ramp from this point and moves to the right, that would be a velocity v0 square plus 2a delta x, and we're searching eventually for delta x, isolating for delta x, taking this to the left hand side and dividing by 2a. Then delta x is given by minus v0 square divided by 2a, and we have determined the expression of the acceleration to given by that, minus v0 square divided by 2 minus mu k multiplied by g, minus with minus cancels, and that would be v0 square divided by 2 mu k multiplied by g, that would be delta x. Now it happens sometimes because delta x here is displacement, it might be positive or negative, and this is equal to the distance because we're traveling one-way direction with no turning points. So basically this is the distance. Just a side remark, if it happens that your displacement is negative, just take the distance to be the absolute value because distance is always positive. And now in part E, which is the final part of this exercise, they're telling you, suppose the ramp now has friction, the same block is projected up with the same initial speed v0 and comes back down the ramp On the axis provided below, sketch a graph of the velocity v as function of time t for the motion of the block while it goes up and back down the ramp, arriving at the bottom of the ramp at the time tf. So basically what we're doing here is that now along the ramp we will repeat the experiment, but now we will switch friction off. So it will go up the ramp, then down the ramp, taking into consideration that we have friction. Arriving at the bottom of the ramp at time tf. So at this point, at this time, it will reach the bottom of the ramp. After going up, it will go down. Explicitly label any intercepts, asymptotes, maxima or minima with the numerical values or algebraic expressions as appropriate. Now here the problem is not symmetric at all. Why? Let me explain. As we go up, what are the forces acting on the block? We have the pull of gravity and the friction, and while it's going down also we have, in addition to the normal push, but I'm not discussing the normal push because the normal push will be always perpendicular to its displacement along the ramp. So up the ramp we have gravity, we have friction. Down the ramp also we have friction, we have gravity, but the thing is that always remember that friction is a variable force, so its direction or magnitude might change depending on the system itself. During up the ramp, gravity would be down and friction will be like that. So in this case we have both gravity and friction, they're acting down the ramp, while as it goes down, pull of gravity will be down, however friction will be to the left, so it will be up the ramp, not down the ramp. So accelerations in both cases are not the same. Let me repeat and say, so the motion in this case can be split into two. Let me say up the ramp and down the ramp, and let's discuss acceleration in both cases. So here we have A up and A down, and let me try to compare these two. During the upward motion, what is the acceleration acting on the block? It's due to two forces, the pull of gravity down and the friction which is down the ramp. However, while it's going down the ramp, we have gravity down and we have friction which is up. So we expect that the acceleration during the upward motion in magnitude is greater or steeper than A down. So I repeat and say, during the upward motion, the magnitude of the acceleration due to both friction and gravity combined would be greater than the magnitude of A down, while acceleration now splits into two between gravity being down and friction would be up. So here, if we want to sketch the graph here, we would expect, so if we don't have friction, we expect that the shape of the curve is gonna be something like that, perfectly symmetric between this part and this part. However, now if we want to sketch it, we need to do like this. Starting from minus v0, it would stop at the top of the ramp at a time which is less than half the time required because acceleration is stronger. So this is minus v0, and upon reaching the bottom of the ramp back again, we would expect that it would be something like this. So if you notice that the steepness of this curve depends on the acceleration, this is more steep than that, and the final velocity at the end of the ramp would be less than in magnitude compared to this one because we lost some speed due to the friction on the ramp. Okay, so this is so important. Whenever we have a ramp and we have friction, the upward motion is not symmetric to the downward motion. Then that's it for me in this video, guys. See you soon in a new one.